In the previous recordings, we proved a theorem that says if F is a field, then the only ideals in F are the trivial ideals, the zero ideal in F itself. And we also proved a converse, which we called converse 1, which stated if R is a commutative ring with multiplicative identity, and the only ideals in R are the trivial ideals, the zero ideal, and the ring itself, then either R is a zero ring, in other words, a ring with one element, or R is a full-fledged field. In this particular video, what I would like to do is try to strengthen converse 1 by weakening its hypothesis. In particular, what I want to do is I want to try and think about what if all we know about R is that it is a commutative ring? In other words, suppose we drop the hypothesis that R has a multiplicative identity element. Can we still get some kind of a meaningful converse? So what I want to do is, in this particular video, I want to assume that R is a commutative ring, and all I know about R is that the only ideals of R are the zero ideal and R itself. And the question is, can we still force the conclusion that R is a field? And so what I want to do is I want to investigate this idea fairly carefully. So we are going to let R be a commutative ring, and we are going to go ahead and assume that R is not the zero ring, and we're going to assume that the trivial ideals are the only ideals that R has. So the zero ideal in R are the only ideals inside my ring. And I want to think about what can I say. Well, since I know that R is not the zero ring, I know that R has non-zero elements. And the real question is what can I say about those non-zero elements? Well, one thing that I can say is, regardless of what element I pick in R, I know that the principal ideal generated by R is either the zero ideal or the principal ideal generated by R is all of R. Now I kind of want to think about non-zero elements and where we're looking at. And one thing that I want to be kind of thinking about is that it'd be nice to know if one pair of elements could multiply together and create something other than zero, because it turns out that if everything times everything is equal to zero, that's not a very interesting ring. So let's make another assumption. Let's assume that there exists A and B inside our ring such that A times B is not equal to the zero element. And one thing that I do want to notice is that this will immediately imply that A is not zero, and it will also imply that B is not zero, because if either one of them were zero, the product would be equal to zero. So now what I want to do is I want to think about this particular non-zero element, AB. And I want to realize that it is an element in one of the principal ideals that I know about. So let's look at this. If I look at A times B, first of all, I know that it's not the zero element, but I also know that it is in the principal ideal generated by B, since A is inside my ring. And that's enough to say that the principal ideal generated by B is not the zero ideal. And so that says the principal ideal generated by B is all of R. And I want to think about what that means. Well, let's look at that. Now, since we know that the principal ideal generated by B is all of R, and we know that B is inside R, that implies that B is inside the principal ideal generated by B. So that says that B is equal to R1 times B for some R1 inside R. Now we also know that B is not 0, and consequently this product R1 times B is not 0, and that's enough to say that R1 is not going to be equal to the 0 element inside our ring, and that's going to be important in a few minutes. Now what I want to do next is I want to let little r be an arbitrary element of capital R. So I want to stress that this is an arbitrary element of R. Now, since the principal ideal generated by B is all of R, our little r can always be written as R something, that I'm just going to call R hat, times B for an appropriate R hat inside the ring R. Now look at this. I want to know what happens when I multiply R1 and R together. Well, R1 times R is going to be R1 times R hat times B. But we're in a ring, so we can reassociate and get R1 times R hat times B. But it's also important to remember that R is a commutative ring, so we can swap the order of these two elements. In other words, we can write this product as R hat times R1 times B, and we can reassociate. And I do want to make the note that this is because R is commutative. But R1 times B is nothing more than B. So we've now got this to be R hat times B, and R hat times B is just R. So R1 is acting like a multiplicative identity. And if we look at the product going the other way, well, R times R1, we're in a commutative ring, so this is R1 times R, and that will be R, we've just shown that. And what this says is that R1 times R is going to be equal to R for all R's inside our ring R, because we chose R to be an arbitrary element of R. And that says R1 is a multiplicative identity for our ring R. And of course, we already know that R1 is not equal to the 0 element. So R1 is a multiplicative identity inside our ring R, and it is not equal to the 0 element. In other words, what we have done is we have shown the following lemma. So we just proved this lemma. And let me state it as a lemma. If R is a commutative ring, and there exists A and B inside R such that A times B is not equal to the 0 in R, and the only ideals inside R are the trivial ones, namely the 0 ideal and R itself, then R is actually a commutative ring with a multiplicative identity and that multiplicative identity is distinctly different from the zero element. So what I want to do now is state a new converse for our main theorem about fields. And I'm going to call this converse converse 2. Let's let R be a commutative ring and we're going to assume that 0 and R are the only ideals of R. And if we have two elements inside the ring with their product not being equal to the 0, then we know that R is indeed going to be a field. And the proof of this is actually very short because we can use the lemma and converse 1. So from the lemma, we know R has a multiplicative identity. So that means that we can use converse 1. So converse 1 applies because, let's see, I want to make that read just a little bit better. So converse 1 applies because we now have R is a commutative ring with a 1, and the only ideals are indeed the trivial ones. So converse 1 implies R is either the 0 ring or R is a field. But lemma 1 says that R has a 1 element that is known to not be the 0 element, so that says R is not the 0 ring, and hence R must be a field. And that ends the formal proof of this converse. I do, however, want to kind of wrap some stuff up with a few observations. So the observations are going to be about the two converses. In converse 1, we have to have the hypothesis of converse 1 is that R is a commutative ring with an identity element and only the trivial ideals. And the conclusion is that R can either be the 0 ring or R will be a field. And in order to use converse 1, we have to know that there is indeed a multiplicative identity inside the ring. Now in converse 2, what our hypothesis is that R is a commutative ring with a non-zero product. We just need to have an AB that's not equal to 0. We need a product AB that's not equal to 0. And of course, R has only the trivial ideals. And the conclusion is that R actually is going to be a field. So basically, Converse 2 says if I can find a non-zero product in a ring that is commutative and has only the trivial ideals, I will indeed have a field. And that is a fairly general converse for our proof about fields having only the trivial ideals. And that ends this video.